Hi everyone, welcome back to Coding with Bharat channel. So today we are going to dive deep into one of the Uber's blog, right? So they have tried to put in how they went ahead building a routing engine to predict the ETA for all of their rides, right? So you would have seen that once you book a ride, you are shown that okay, you would arrive at your destination in probably 20 minutes. So to get that 20 minutes more and more accurate, they have engineered, I would say, a very sophisticated routing engine from scratch, and that is what is being talked about in this particular blog and a subsequent recent blog that they have written. Okay, so yeah, first thing that they have started with is saying that okay, this feature that they had tried to launch, the routing, was a feature launched way back in 2011, right? So when it was launched even in 2011, they went ahead with an open source routing engine, OSRM. So yeah, so let's go through the documentation of it like a little bit to get to know how it was there earlier and what challenges that they actually face. So this is basically your OSRM API documentation. So even you can try hitting these APIs, these curl requests. I'll put this link into the description. You can see here that there are four major services, actually five, six major services that these guys provide, out of which a few of them were very helpful and useful for Uber. First being route. So what does route do? So route request, you can give two coordinates. Let's say we try to give a coordinate of India Gate in Delhi and try to give a coordinate of Gateway of India. So this route will try to put across the route, right? The route means the actual path that you will take to reach from India Gate to Gateway of India, right? So maybe let's look at one of the examples also of this. So let's look at response of this route. So whenever you call this route for two locations, it gives you something like this, right? So it talks about the distance that you would need to travel in this route. It also talk about the duration, the estimated time of travel, right? And it also talks about the different steps that you will take in to reach that particular position. So for example, if you look at the object of route step, like each step, then it talks about that okay, when you are driving you need to go left, go straight, go right, and whatever, right? So yeah, the route feature entirely gave us that okay, if you want to reach from point X to point Y, how much time it will take, how much distance it is, and what are the steps that you would need to take to get to that particular position. Okay, apart from this route there were a few more which were actually very helpful for Uber. The next one important one being nearest. So you can imagine, right? So when a person is trying to book their particular cab, so you need the rider location or the coordinates of all the drivers, and then probably find the nearest few to basically show them a notification that okay, this person is trying to book a ride for some XYZ place. So actually if you look at it, this nearest service also does something like this, that okay, it takes a coordinate from the street network and returns the nearest n matches, right? So nearest n places it would give you. So yeah, all these services were there as part of this open source library, and Uber relied on that. But soon they realized that there are a lot of things here which are problematic. So apart from this service, they also started collecting data. So for example, initially they would have served just based on this service that okay, the ETA is 20 minutes. But let's say there are 1,000 people that have gone from, let's say, India Gate to like some other place like say Cyber Hub. And for all of them, it took about 40-45 minutes at a particular time also, let's say in the evening. So if that kind of data is very prominent throughout the Uber history, then they can modify their whatever result this open source is giving to actually give a more accurate result, since they have already seen that it takes about 45 minutes to go from this place A to this place B. So yeah, that is what they have written as the next part here, that based on Uber's own historical data of similar routes in at the same time and of the same coordinates, they used to made adjustments to whatever this open source libraries used to give. This service that they had built was called Goldeta. So Goldeta essentially used to look at the open source results plus historic data to finally come up with the best estimate that it can get to show it to the user. Okay. Now, with this solution, the main problem that they said is the problem of cold start. So what does cold start problem mean? This is actually a common problem in software engineering. You would have heard of cold start caching, right? So generally what we do when there are a lot of requests coming into a particular API, right? So generally what happens that API builds in a cache, right? So uh, for a general request, the request comes to the API goes into a DB. From the DB it fetches the data and sends it back, right? But let's say now that same API is being called more frequently and everyone is getting that data with the same parameters, then it is a better idea to skip that database and keep something in cache or something in local memory with us, right? So yeah, a lot of people with the high throughput APIs solve the problem of latency using this cache. That okay, common things will try to put in cache so that they can be quickly fetched. Now the cold start problem also comes here. When you launch the API or whenever there is a change, let's say in the API and you relaunch it with the new version, then the cache is virtually empty, right? Or if the service scales horizontally and a new server is brought up, then that new server will not have the cache inbuilt. So the queries that are coming to it will take more time now because they are going to go into the database. And if there are a lot of such requests, then the server might get throttled. Like too many requests might be coming on it and it might not be able to respond. So this cold start problem is common across, I would say, software engineering world. And same they saw here that whenever they go to a new place and launch their Uber services, then they just have to rely on the open source. They don't have any historical data and they cannot do anything about it. Okay. So yeah, that was a major thing that is mentioned here about the cold start problem. So with this, and to increase the accuracy a bit further, and to involve a lot of more newer things, like for example, they came up with Uber Pool, where a lot of other peoples can club together and take a common cab, right? Or they even have started Uber Eats, where they might be trying to find the best route for each of the driver from different restaurants, different locations, right? So to add that flexibility, to be more accurate, and to solve the cold start problem, that if they are rapidly launching in new places, they cannot give poor estimates to this ETA, right? So due to all these three problems, they went ahead with creating their own routing engine from scratch. Okay. So that is the next portion that they have mentioned here, that how do you go ahead and build your own routing engine. So first thing that they are seeing is that the entire country or the entire world for that matter is generally organized as form of a graph, right? So I hope everyone is already familiar with what a graph is who is watching this video. If not, it would be a good idea to quickly check through, right? So what is a graph essentially? Just to summarize it in a small fashion, there are some nodes and those nodes are, you can say, linked together as form of a, with the help of edges, right? So all the major locations, landmarks, places, they can be thought of as nodes in the graph. Like each of the intersections of the road from where three roads go or four roads go, those can be thought of as these nodes. And the paths going from it or the roads coming out of it, they would be called as the edges. So essentially the entire world can be thought of as some nodes, which are all the intersections, all the checkpoints, all the landmarks and everything, and different roads coming out of these landmarks and intersections. Okay. So yeah, that was the first thing. We have modeled it like a graph. Now, whenever a person wants to go from a place A to a place B, it is like we are trying to find the shortest path from A to B, right? Wherever we are to wherever we want to go, we want to find the shortest path. Okay. But now, are all the edges or all the roads, should they be considered equal or should they be considered different? So the answer is obviously they should be considered different. Each of the location might have different lengths. There might be different traffic situations on those roads, right? And things like that. So not all edges are same, but each of them have some weight associated with it. That weight could be the distance, the weight could be the time, the weight could be almost some combination of it as well, right? So yeah, let's just go over the blog again to read it. So basically it says that, yeah, so the old version of theirs, Goldeta, served us well, but they wanted to launch Uber Pool, right? Uber Rush, and yeah, with all these things, cold start problem and all those things, it became clear that they needed a dedicated in-house routing engine, and that was called Gurafu, and that is what they tried to build from scratch. Okay. Now, first thing that they've said is that the essence of it was that the whole network is being modeled as a graph. Nodes are the intersections, edges are the road segments. Next thing, the edge weight represent a metric of interest, either the distance or the time taken or a combination of both. Right. This is what I've talked about. That yeah, each of the edge have a distance or a time for it. Okay. Then they've said other things like one-way streets, some of the turn restrictions that okay, you cannot take a left turn, you cannot take a right turn. Cost of each, like if there is a red light, there is like 50% chance that you arrive with a red light, right? So yeah, those kind of things were also taken in. Plus speed limits. Although the traffic is low, the distance is high, but still, if there is a traffic limit, people will drive at a slower pace. So those kind of things were also modeled into this graph. So to get that edge weight, it's actually not just a single number like it normally is. It is a combination of a lot of metrics. Okay. They have also mentioned that okay, this is not the only way. Some companies have tried to model segment as nodes, like the intersection as you would say intersections as edges, and the roads as nodes, right? So they have flipped it. Okay, cool. So the second one is called edge based representation, but they have not used it. They have used the previous one itself. Okay, cool. They said that the first thing that comes to the mind is if you want to calculate this shortest path, use something like Dijkstra's algorithm, which can be used here, right? So what is a Dijkstra algorithm? Dijkstra is essentially a greedy algorithm where, let's say you want to go from A to B. From A, you look at all the intersections and you first try to go through the shortest one. Then from there, again, from all the intersections now available, you go to the shortest one, then go to the shortest one. And finally, at some time, you will try to arrive at the destination. Okay. So, just to give a little more clarity, let's take this graph only, right? And let's say each one has some edge weight. So, let's say this is having weight 1, this is having weight 5, this is having weight 2, this is having weight 7. And let's say we want to go from this A to, let's say, this B. So first Dijkstra, what it would say find the shortest out of the connecting edges from A. So shortest is this 2. Now you have A and this node in picture. Now try to find the shortest further from them. So now we have options of 2, 5, 7 and 4. Again we take this 2 and with distance 4 we arrive at this B. So yeah, that is the main idea of Dijkstra, that you always try to greedily take the shortest one, shortest possible one, and then try to see when you can arrive at B. The problem with this algorithm is, in worst case, you have to explore the entire graph and the complexity goes to about E log V, right? We use priority queue and we have some elements in it and we visit every edge. So for every edge, we do an insert and removal from priority queue. You can check out the algorithm if you want. And yeah, the complexity essentially turns out to be E log V. Now, with a graph equivalent to the world, E log V is really not possible to be taken, right? Like number of edges in the world, that would be super huge. And to calculate every path, if you are using this much time complexity, then it's virtually not possible. And that is what they have mentioned in their blog as well. That yeah, however, in production, Dijkstra and any algorithm that works on top of unprocessed graph is usually too slow. As you can see, the complexity E log V for a world like graph is not possible. So now they have said that this OSRM, the open source that they were using, used contraction hierarchies. So let's talk about what contraction hierarchy is also to get more idea on it. Okay, let's talk about the idea of contraction hierarchy. So the idea on which it is based upon goes like this. So let's say we are talking about a real world network where there is a main highway, right? So generally, if you have gone through any highway, how what happens is there is a main city, let's say something like Delhi, and this highway is connecting another main city to it, right? For example, let's say we are talking about the highway that takes 2 minutes. So now what will happen? A lot of internal turns are there to go to different small villages, small towns, right? That there are cuts to it basically. So the contraction hierarchy approach says that these nodes that are the ends of the highway are more important nodes than the others, right? So basically what we try to do, we try to define a node importance value. And how do we define that? We define that by looking at that, okay, this particular node or intersection is part of how many shortest distance. So if you think about it, these nodes that are there internally on this highway, all of them would be part of all the shortest distances that take anyone from this city to this city, right? Anyone going from Delhi to Meerut has to go through these nodes. So these nodes will have higher importance than other internal nodes, right? Because they are connecting more, you can say they are being part of more shortest paths. So node importance directly ties in with number of shortest paths node is part of. Okay. So what we do a pre-processing on this graph. So before we go on to running our queries, we do a proper pre-processing on it. In pre-processing, we try to define for each node its importance value, right? Which is the heuristic value for it. Okay. So the idea is that if we now know the importance value and we are trying to, let's say, find shortest path to some place in Delhi to some place in Meerut, then we would not go and explore each and every path, but we'll first try to go through the nodes which are more important than the current node. So if you think about it, if let's say I'm talking about a small house or small street in Delhi, that would be part of lesser shortest path than a main road. Then the main road nodes would be less having lesser being part of lesser you can say shortest path than probably some major road like ring road. Then those would be part of again smaller than the highways and so on and so forth. So the idea is that from smaller places you'll first go to like more important nodes which are part of the larger places, then more important, and so on and so forth. So you what you try to do, you do a simultaneously search from both source and destination to arrive at the most important nodes of it. So quickly basically find the path to this highway node. From here also find the path to this highway node, and then these can be connected. Okay. So now we don't use Dijkstra, but we do a search based on importance, that those which are more important would be gone to first. Okay, so that avoids going into the search of all the smaller, you can say, lanes that would be there in a particular locality of Delhi, but quickly you move on to main road, then quickly you move on to the further major road, and so on and so forth. Okay, so with this idea of contraction hierarchy, Uber was able to achieve much better results. But the problem with this contraction hierarchy is that the pre-processing step is done once, right? Now, and this pre-processing step is very costly. We are going to process the entire graph and try to find importance of each of the nodes. Because of this being costly, any changes in the graph are very complicated to accommodate. So as an example, let's say this road gets closed. It will still keep on showing you that path, right? Because if this road is closed, now we need to go ahead and recalculate the entire importance values for the entire graphs, right? Or let's say one particular road had a pothole or had some accident, and because of that there is a lot of traffic going on it. So now the cost of this path will change, and the importance value, because it will now start becoming part of lesser and lesser shortened paths, shortest paths. So importance value of it will decrease, and others importance value will increase. So again, a huge pre-processing would need to take place, and these kind of things are very common in cities, right? Like places can get blocked, places can get having a lot of traffic, accidents can happen, all these things can happen. So the problem with this approach is that it is not reactive in nature, right? Like you do pre-processing, but then it is fixed. Okay, so yeah, it like Uber has talked about this here, that okay, contraction hierarchy. They said that systems based on this achieve fast performance. Queries are fast, right? Taking just a few milliseconds to compute out, because importance value, quickly you will jump in importance value and finally reach the destination from both sides, right? But because this pre-processing step is very slow, it is very difficult to make real-time traffic adjustments. Okay, so they said that their algorithm on contraction hierarchy roughly took 12 hours to compute the contracted graph for the entire world, right, or entire system that they were using. Okay, so that means that this data would quickly get outdated as soon as a new thing is added. Okay, cool. So they tried doing some pre-processing and tweaking, right, to make this happen. That okay, we'll only do adjustments in a small locality or things like that, right? Yeah. So that is what they have talked about. That making contraction hierarchies dynamic. So yeah. So as they have mentioned, one drawback of this was when weights are updated, the pre-processing steps needs to be run for the entire graph. So instead of that, what they went ahead with dynamic updates, where the ordering they tried to maintain the same, like the ordering of it is same. uh yeah, only internally the edge weights are changed, right? So for example, if one highway is blocked, probably they'll try to take another highway, or one main road is blocked, the other main road they'll try to take, or something with the similar importance that will have lesser weight. So still some improvement can be brought about on this real time traffic update. Okay, so yeah, basically they said that this decrease in pre-computation helped significantly, right? Now it just took 10 minutes to dynamic update. So they said 10 minutes is still too much of a delay for the regular traffic updates that are coming. So ultimately this path was a dead end. Next thing they tried sharding, that we would break the entire graph into portions, geographical locations, right? And only recalculate for a particular shard when traffic is updated, right? So the problem with this was that it required quite a bit of engineering for infrastructure to work, because they had to do it in such a way that still most of the common paths that people take are not impacted that much, right? Second, they said that this would introduce bottlenecks in the cluster of those regions that have, you can say, more significant traffic than the clusters of those regions that have lesser, right? So yeah, that is what is there. And too many requests during peak hours, so those clusters of a particular region might get jammed packed with a lot of requests. Okay, and the other servers would not be able to take those requests because they are running a different shard of the graph altogether, right? For example, if some server is running only the shard of, let's say, some West Delhi part, right? So now, if a lot of, or let's say South Delhi part, so if a lot of people are traveling from Gurgaon back to South Delhi at a particular time, let's say during the office hours, then that server will get a lot of Uber requests and it will not be able to handle it. Okay. Third thing that they tried was A star algorithm. So let's quickly talk about A star algorithm next, which is a heuristic based algorithm. So yeah, A star search in general works with the idea of heuristics. So what are heuristics? Heuristics we have already seen also in the previous approach as well. But the idea of heuristics is that at any place, if you have multiple options, you try to give a weight to each of the options, like or approximate a weight to each of the options. So, like we saw, we gave an importance value to each of the different edges that we can take and try to take that edge which gave us the most importance value, right? So, similarly, what A star does, let's say if we have a graph and we want to, let's say, reach from some value A to some value B. Now we have different path options that will be coming out from this A. So let's say this A is an intersection having four paths. Now if we want to reach some location B and we have these four options, A star, what it does is it tries to figure out which path brings you more closer to B. So as an example, taking this particular path, we can easily compute we know the latitude longitude of this position, latitude longitude of this position, so we can easily compute the overall distance, like direct distance from this point to B, direct distance from this point to B, this point to B, this point to B. So the idea is that we will go through that path first, or that path will have a smaller heuristic value which brings us the closest to B, and we'll try to explore that option first. So first we'll go through this option, right? So basically, A star algorithm is a quicker form of Dijkstra. In Dijkstra or in other BFS or DFS algorithm, you'll explore every option. But here you'll try to prefer that option which brings you first closest to B. Okay. So yeah, that is about A star. So they said that they tried to go ahead with A star, where they talked about that, okay, for real time updates in a small scale, they tried A star algorithm. So at high level, they said Dijkstra's plus heuristics is what A star becomes, right? So Dijkstra, but taking into account this heuristics, that which edges are bringing you closer to your actual destination. Okay. Now, with this, they could easily update the edge weight because on the fly they are calculating the route. It is not like they have pre-computed it or pre-computed anything. On the fly, whenever the query is, they'll calculate the result, and whenever there is an update in traffic, they can simply update that traffic, right? So that's perfectly okay. Okay. So yeah, A star worked for this dynamic idea. But they knew that A star was a temporary solution because it's really slow for long routes. So as soon as long routes come into the picture, you are anyways going to have multiple paths which will make only a significant difference in the actual distance. So you'll have to explore all of them, right? So because of these limitations for a huge graph, right, a road would probably just cover a small fraction of the actual path that you are covering in, let's say, an intercity travel. So yeah, it became really, really slow for long routes. Okay. So even they said A star with landmarks, right, which made use of triangle inequality. So what is triangle inequality? If there are two paths taking to a position and third path also, triangle inequality, if you remember, like if there are, this is a mathematical thing. So there are two paths that also arrive at the same place and one direct path which also arrives at the same place. So obviously this one will be smaller because like they will be forming a triangle and sum of the two sides of the triangle A and B is always greater than C. So they would avoid such routes which take to the same place based on like where there is a direct route already available. Okay. So even they said by these optimization of using triangle inequality, optimization of noting down the landmarks and trying to first reach the landmarks, they were still facing a slowness in this real-time calculation algorithm. Okay. Specifically for long distance trips. Okay. So now what they did, a classic thing, combine these two, right? So they needed the best of the both world. So they needed pre-computation to make things fast and the ability to update the weights, right? So yeah, they had to do a combination of both the approaches. So so what did it? Their actual algorithm divided the entire graph into layers of small cells which are independent of each other. So try to divide the entire graph into layers, and the pre-processing step now runs in parallel, right, to make it even faster. So for each cell, the pre-processing happens independently. Okay. And yeah, so basically in 2015, they globally launched their entire routing algorithm, which was a complex combination of these two algorithms. Okay. Great then. That is what they have mentioned. They have not mentioned the exact way in which they combine these two algorithms. But my assumption is for long routes, they would be preferring the pre-computed paths at some places. For shorter paths, they might be doing A star search, something similar to what we had seen. Okay. Now, next thing that they say is, they said to measure the accuracy and measure that how far they have gone. They have also integrated entire Kafka pipeline to note down the metrics that okay, this was the estimated time, this was the actual time, and the difference, and have alerts on it, right? So all that obviously was part of it because analyzing the data of how your algorithm is working is equally important in a real world software problem. Okay. Yeah. So yeah, that is what this entirely talks about. And then they said that they are now evolving this algorithm for Uber Pool and Uber Eats. Okay. There is one more article of theirs, which is more recent one in 2022 article, which talks about that now they are predicting arrival times using deep learning, right? I'll probably make another video out of this because this would involve a lot of concepts of machine learning and yeah, mathematical encoders, decoders, and all of those things into the actual yeah algorithm, right? So yeah, we'll make a separate video about this. But yeah, that was the main idea of the first routing engine that Uber built without any MLAI with using proper algorithms, right? Great then. I keep on doing these discussions at least one per week where I cover up such blogs, some such complex blogs of different companies and try to break it down for you to understand. So I'll link all the docs in the description. Do like the video if you were able to get the idea, and do subscribe to the channel. If you're new here, we'll keep on doing this further. Great then. See you guys in the next one. Bye bye.